Hi, I'm Shekhar Pradhan. I'm a faculty member of the Data Science Institute. I am very happy to welcome Omri Suissa, who is a postdoc and a visiting scientist in the Conversational AI lab at DSI, which I head. And we are working busily on all kinds of research projects. And he has I've heard this talk, I think 3 times, and it's a very good talk, introduction to efficient LLMs. So, and he takes this very seriously. He's practiced it innumerable times. So it'll be a flawless performance. Go for it.
All right, thank you. All right, so yeah, let's start. So today's talk is about efficiency in the context of LLM. And it's an introduction talk. And by the end of the talk, I hope you will be able to run and train LLM with less resources. So this is the promise of this talk. Before we dive in, right, so a bit about myself. I'm a postdoc, and as Shekhar said, in the AI Conversational lab. We're working in the lab on a fascinating research on linguistic supervision of multimodal embeddings, which is super interesting if you care about that. My PhD was on question answering, on multiple data structure and small models. I also serve as the VP R&D at Klimesh that works in the AI space, and have about 2 decades of R&D experience to enterprises mainly. All this to say that you're more than welcome to engage with me on these topics now or afterwards. I'm always happy to talk about that. All right. So today's talk is about efficiency in LLMs, right? So what are we talking about when we actually said efficiency in the context of LLM? The first thing that comes into mind is latency, right? We want LLM to be fast. The second thing that comes into mind is usually resources. We want to use less GPUs. GPUs cost a lot, as you probably know. And we want to train model or inference model with as minimal GPUs and minimal resources as possible. And the third thing that comes into mind, I guess, is data. We want to need as minimal data as possible in order to train our model, because data curation is also very hard and expensive process. The second question we need to ask ourselves is, when do we want this efficiency to happen? So one place is inference. We want our model to generate output faster or with less resources and so on. And the other place is doing fine-tuning or training. Now, most of the methods I'm going to show you today are treating only one of those processes, only inference or training, not both. Some of them treat both, but most of them only treat once. And some of them are even undermining the other process. That means we can have a model that is very efficient doing fine-tuning, but going to be less efficient in inference and vice versa. So you need to keep in mind where exactly you want this efficiency to happen when you talk about efficiency in LLM. So before we go into solutions, let's talk about the problem. So why do we even talk about this efficiency in LLMs? And the root cause is the scaling works. I guess you all heard about scaling laws, right? The combination between how much resources we have, how much data, and the size of the model. So in general sense, if I'm simplifying that a bit, the larger the model, assuming that you have the data and resources, it's going to get a better accuracy. And a simple demonstration I found online is this visualization in size between GPT-3 and GPT-4 in the context of number of parameters. So the larger the model, we get better accuracy, but we get less efficiency. Now, there is room to talk about other architecture except transformers that may be less computational sensitive to size, but this talk is about how to make transformers more efficient, right? So I assume, by the way, that you all understand transformers architecture, basic training and inference processes, and know Python, but that's it, right? Yeah. And by the way, you can even buy online t-shirts of scale is all you need for AGI. So if there is a meme about that, it must be true. All right. So before we talk about how we handle with this whole phenomena of scale as much as you can, let's understand how we actually measure model size and how it affects our resources. That means how much resources we're going to need depending on the model parameters. So let me add a pointer. Right. So let's say that we have 1.3 billion model parameters. That means we have 1.3 billion parameters. We have all those parameters are stored in a 60-bit float, and our secret length is a 512 size. So let's see what's going to be the estimate size of that model. And I'm emphasizing that it's an estimation. It's like a back of the envelope calculation. It's not exact, but it's enough to understand what we are facing here. So 1 gigabyte going to be for CUDA. And there's nothing we can do about that unless we work in NVIDIA, but let's take that as for granted. 2.6 gigabytes going to be our model weights. And that's the size of our float times the size of our parameters. And we have 1.3 billion parameters. So that's going to be 2.6 gigabyte. Another 2.6 gigabytes going to be our gradients when we train the model. And that's going to be the size of our floats times the size of our trainable parameters. And here we assume that we train the entire model. We will not assume that later on, but here's an assumption. So it's another 2.6. Now the hidden states, which are a bunch of different things, like the embeddings, the positional encoding, the attention matrices, and so on, it takes another about 1 gigabyte per sample. It's very hard to calculate that. I didn't find even one, let's say, reliable calculation, all back of the envelope calculations, but it's generally related to the length of the model. And you can, I put a paper here that talks about that if you want to read it later. Of course, I will post the presentation. So it's explained it in more details. And optimizers takes, most modern optimizers, for example, like Adam, takes about 2 times the size of the trainable parameters. Sometimes this goes unnoticed, but in Adam, in order to calculate the learning rate, needs to store 2 copies of the gradients, and that's mean another 5.2 gigabytes. So in total, if we sum everything, we're going to have a model of about 12.4 gigabytes. Just to emphasize on the estimation here, when you upload this model to a GPU memory, it's going to take about, in real life, about 11 and some. So it's the same scale, and you get the idea. Now, this is for bed size equals 1. In real life, we use bed size of 64, 128, 120, 256, and so on. And moreover, this is an 1.3 billion parameters model, which is quite small in today's terms. For example, I guess you all heard about Llama, by Facebook. So it comes from sizes from 7 billion to 405 billion. The 405 billion parameter model needs about more than 3 terabytes of GPU memory in order to upload to memory to run. So to train. So yeah, it's a big problem. So we have 4 variables here. We got the float size, we got the number of parameters, we got the number of trainable parameters, and the length of the model, right? So keep in mind, we're going to come back to that later on. So we know our challenge. What are our solutions? So this is an introduction to the topic. So I'll try to cover as many methods as possible to give you a broad picture of this space. But if you want me to focus on something more specific, please let me know. So when we talk about improving efficiency in inference, we have generally two types of method that improve memory and method that focus on latency. Of course, that reduction of memory improve latency, but that's to say that latency-focused method not always improve memory. I will explain that later on. And we're going to cover fine-tuning training. We're going to circle back to some of the methods we see in inference and talk about parameter efficient tuning and all these sub-methods of that. Right. So let's dive into inference. Before I start, any question about that? Right. Good. So the first method I want to discuss is knowledge distillation. Here we assume that we already have a very good model, right? For example, let's call it GPT-6. And it's large model, and it's cost a lot of money to run it, and it takes time to output. Now we want to create a smaller model, let's call it GPT-6 mini, that will have the same or similar accuracy to the large model, but will be much more efficient to run. So we want to mimic the output of our model, of a larger model, with what's we call a student model. So we have a teacher model, which is a large model, and a student model. Now the assumption here is that while we need a lot of weights doing training, once the model learns the underlying distribution of our task or our data, then we don't need as much as weights doing inference. So we have three main options how to do that. The first option is response-based distillation. Here we take the teacher model as a black box. We don't care about the teacher model internals. We just take the output of the teacher model. We take the output of the student model, and we combine between our task loss, which could be a classification, for example, and a distillation loss. A distillation loss is a loss that computes the distance between the output of the two models. It could be L2 loss. We can convert the probabilities into soft tables and then use cross entropy, for example, and so on. And the idea that the student model will not only learn how to perform the task, but it will also learn how to mimic the larger model, right? Yeah, makes sense? All right. The second option we can do is feature-based distillation. Here we need to understand the internals of the teacher model. It's no longer a black box. And what we try to match with the distillation loss is components within the network. For example, layer by layer. We can match the first layer output to be the same or similar to the first layer output of the student model. The second layer output of the teacher model to similar to the second output, and so on. So the assumption here that if we give those signals in the loss, it will be easier to the student to learn rather than just see the end response, right? Now, when we say components, it doesn't have to be layers necessary. It could be also attention matrices. It could be a group of layers, and so on. So the idea here is to give signals, during the inference, not only at the end. By the way, I didn't say at the beginning, we freeze the teacher model. We only train the student model. Yeah. And the third option is relation-based distillation. Here we don't care to map between each output or each component within the student teacher model. We care to reduce the distance between the relations between outputs of the teacher model and the relations between the output of the student model. So we try to capture here a relational knowledge that exists between how the teacher predicts output its prediction. All right. Any questions?
I guess you could combine the three approaches also, great hybrid.
Yeah. Well, you can look at the response. Sorry, the question was that if you can combine the approaches. You can look at response-based distillation as one particular case of feature-based. You can see the response as a feature, so you can combine them. The relation distillation, both. I didn't see a paper that combined. In theory, it could work, but I didn't see a research say that.
And it doesn't work.
I don't know. Yeah.
Can you give some intuition? I mean, maybe you're not going to cover them deeply, but with feature-based distillation, you're using information not available in the training data, weights, whatever you read. In response-based, you said you're trying to use a loss that combines both the output of the model and performance of the task. But that presumes that you still have access to some kind of labeled training data or something to do that. And so there's a question of like, well, how much should I just train the smaller model on the task itself, not even worry about the teacher? What's actually happening to make an improvement here?
All right. So the question was about how, if I simplify that a bit, but how the distillation loss actually improve the outcome of the student compared to just train it on the classification loss. So the intuition here, or the concept here, is that there is so much you can learn from the data itself, because we're training the student model, right, on our data set. But there are things that you cannot learn from the data itself that can only be learned from the teacher model. It could be reasoning features. I'm way simplifying that, but it could be reasoning features that the student model could not get alone unless you see examples. So you can see as the teacher model as a way to produce a more nuanced output of how the output should be.
Right. So, I mean, to be specific, is the presumption here that the teacher model is, OpenAI, it had access to the full internet, and your application loss is on a data set of just some corpus that's specific?
Yeah, exactly. Yeah,
the data is not the same?
No, data is not the same. We assume that this model saw everything, and it's always correct, which of course it's not true. I mean, it may be wrong, but this is the assumption. And our model see our data and more prone to errors. Yeah, this is the general assumption here.
So it's kind of like an indirect fine-tuning.
Yeah, you can call it that. Exactly.
All right. Even if it saw the same data, the assumption is that the larger model picks up things that the smaller model does not, right? And therefore it's still worth doing it.
Yeah, definitely. It could work on the same data, but usually, from what I saw in real life, you use like a large model trained on the internet and try to train on a small data set. All right, so if you go back to our formula, then what we're actually affecting here, comparing from the teacher model to the student model, we reduce the parameters, we reduce the trainable parameters, and reduce the length of the model because everything is smaller. All right, so I will not go, it's supposed to be a very light talk, so I will not go line by line on code, but just to give you examples of open source framework you can use today that already implement those methods and how you can implement yourself. So I guess you all know Hugging Face, and they have a distillation trainer, which is a class you can just send the teacher model and the student model, and it will do response-based distillation for you. So super easy to use. And if you want to implement it yourself, it's also a very simple concept. You can have a large model that will be on eval. We're not going to train that. A distillation model will be on train. And then we can just convert the large model output to soft labels. And the distillation, we can combine our training loss, our task loss, and our distillation loss will be some metric between those two labels, again, like cross entropy or whatever. So it's very easy to implement, but you don't have to, it's already exists in open source community. All right, the next method I want to talk about is quantization. Quantization is actually a form of compression. We want to compress our model, and to do so, we want to reduce the size of the floats, because most of our data is actually floats, right? So the size of numbers is 2 to the power of that size of a number. For example, if it's float 32, the range will be 2 to the power of 32. If it's the int 8, the range will be 2 to the power of 8, right? So we can reduce this range. And how we can do that? We can simply scale it, right? Simple as that. We take the ranges of 2 numbers, we get a scaling factor, and then we can divide our number with a scaling factor, and we want to keep 0, 0 because it has a special meaning, and we can just simply scale it. So if we scale all our weights, we just reduce dramatically the size of the model, and it's linear. So if we reduce from 64 bits to 16 bits, you can see the reduction is linear and dramatic. However, when we do that, we also introduce errors, like most compressions. And how we can measure this error? If we take our matrices and we quantize them and dequantize them back, we can calculate the difference between them, and this is going to be our quantization error, right? So what caused quantization error? Mainly outliers. If we have most of our values in our weights have similar distribution, but we have some outliers. When we scale them, we're gonna completely raise this distinction between different weights. So what we can do, we can just clip the range. For example, say that everything above 5 is 5, everything below -5 is 5, and so on. And then you can see that the distribution will be much more similar to the original distribution. So we just solved the problem, but we actually introduced another problem. How do we select the clipping value? How do we select the min and max values? So in order to solve that, there are two main methods. One is doing that with a calibration dataset. That means we have our two distributions. We want to minimize, make them as similar as possible. So we have a calibration dataset. We run the calibration dataset. We run our model on the calibration dataset, and we see the actual values of the tensors. And now we know what is the right min and max to use. We can have different techniques to select outliers, but it's a standard procedure. But the problem is, even though it's a very lightweight, a simple method, the problem is that it may fit to our calibration dataset, and that's not going to fit to any other dataset we're going to meet in the future. So another technique is called dynamic quantization, that we actually quantize the weights beforehand, but we don't quantize the activations. We keep them in high precision, float 32, for example, and then only in runtime, we see the min and max of what's going through our layers, and then we quantize in runtime. So it's done layer by layer. So this is an example of what I said at the beginning of a technique that will reduce memory, but it will increase latency because we now have another action to do within every layer to quantize in runtime. So it's a trade-off, right? So if you go back to our formula, now we're going to influence or reduce the float size, right? And by that, reducing the total model size. So there are many quantization methods. Some suggest that we will use different scaling per different groups of weights. The research suggests that we use different precisions. That means not just one precision to all weights, but different precisions. You can just ignore or change the weights of weights that are specifically more prone to high quantization error. That means it's the same idea as creating dynamic quantization, but only on specific weights that are presented as an outlier. You can do it row-wise, that means channel-wise, instead of layer, of column-wise. You can ignore quantization of about 1% of the weights that are more important. It's another topic how you select what is more important, but you can do that. And recently there was a paper that a lot of noise in the community of 2-bit quantization, which is super extreme. Now, and by all means, there are so many other methods, but just to show you how much this research is current and evolving, this paper is from like 6 weeks ago, and it's already implemented in the open source community. So yeah. So how you do that? So Torch actually introduced dynamic quantization. Super as that, you can give a model, you can give a type, and it's quantize the activation during training. And if you took a BERT model, small model, in today's world it's already small, you can see the output. Dramatic reduction in memory size and in latency, but small degradation in accuracy. And if you want to implement that yourself, then again, just do the scaling. We get our parameters, we get the mean, we get the max. We can scale that, and then we can just clamp, that means trim, based on our scaling. Right, sorry, questions about quantization? Right, that makes sense? Good, all right. So another thing we can do is we can just speed up calculations, right? Pressing the turbo button on my computer. No, just kidding. But we can have ways to calculate the matrices much more efficiently. First of all, we can do cache. Caching is a simple method. In transformers, we are doing the same calculation over and over again, specifically the K and V in the attention mechanism. So we can just cache that. Of course, we're going to increase memory. but we're going to reduce latency. We can do approximation of attention. That means lowering approximation. Now I'm going to talk about it more in detail when I talk about lower on parameter efficient tuning, but we can just take our attention, decompose it, and use an approximation of the result. And a very famous method called flash attention, which actually prevents the materialization of the matrices into memory. That means that when we do matrices multiplication, instead of uploading the entire matrices to memory, we do something that calls online softmax. That means incrementally calculate softmax and only uploading to memory block by block of the attention matrix. I'm not going too deeper because it's really depend on how it works, but it's very easy to use, and it's has 100% accuracy. I mean, no accuracy equation because it's doing the same calculation as softmax would do, but only block by block with attention to the different memories that we have on the GPU. So how can you use that? We have attention implementation in transformers. You can just name the attention you need. We already have attention 3, flash attention 3, and you can use cache when you generate. Will again may increase memory to the cache size, but improve speed. And this should improve 2 to 4 times. This based on transformers measurements. The writers of flash attention said it could even improve by 7 times, but they measured 2 to 4 times and reduce memory, of course. Sorry, any questions about that? Right, good. So the next method, the next method is speculative decoding. This could be the last method regarding inference. And this method going to actually requires to use much more memory. So it's not efficient in a sense of memory of GPU, but it's efficient in a sense of latency. All right, the idea behind speculative decoding is that we can ask a small model, let's call it a draft model, to draft a response, and then validate that with a larger model. So how can you do it? Let's say that we want to generate a 10 token sequence, right? Like a 10 token sentence. So we ask, so we can use the larger model to run 10 times, right? This is the standard approach, generative approach, run 10 times and generate 10 tokens, right? So this is very slow. So we can use a draft model to run 10 times and generate those 10 tokens, right? Which will be much faster. And then in parallel, we can use the target model to validate the response. And what do I mean by validating? I mean giving the large model all the sequence and subsequences in parallel. That means it will take the time of one run. It's in a method called batch processing. I guess you know that. So in validate, we mean that the probability that the large model will assign to every token is going to be equal or large than the probability of the student model, right? So we call it an agreement. The teacher, agree with the student. So let's say we have these 10 tokens and we run the draft model 10 times and we now have 10 draft tokens. And we validate that with the teacher model, and it's going to take us one in terms of latency times. One time, we're going to do it in parallel. And let's say the teacher agrees with the first 9 tokens, but agrees with the first 8 tokens and disagree with the 9th token. All right, so we don't know what's going to be the 10th token. We don't know that because the 10th token is dependent on the prediction of the 9th token, right? But we know that the 8 first tokens are correct. And we also have the 9th token because we know what the teacher predicts that contradict the student. And now we can run one more time the teacher model or the student model, depending how much more we want to generate, and do it again and again. So we just traded 10 times of running the teacher model with 10 times of running the student model and only 2 times of running the teacher model. And when you talk about latency, it's dramatic because the gap between using those models in real life is usually very dramatic, right? And yeah, super simple. When you use transformers, you can just give an assisted model and it will do the drafting and use it as a draft model. All right. So yeah, 2 to 3 times more. So now let's move to how we fine-tune or train our model. And the first thing I want to discuss is circle back actually to knowledge distillation. And there are methods of knowledge distillation that affect training or fine-tuning, eventually affect inference, but also affect training fine-tuning. So the first one is self-distillation. Self-distillation is the idea that while we train the teacher model, unlike the inference when we have a teacher model, now when we train the teacher model, we're going to distill itself to a student model. And the idea is that we do that every once in a while. So let's say that we do it every epoch. So after the first epoch, the teacher model is going to distill itself, and we're going to call that student generation number 1. And then after the second epoch, the teacher model is going to distill itself, and you're going to call it student generation number 2, and so on. So think about student generation number 1. It has the knowledge, the distilled knowledge of what the teacher learns after 1 epoch, right? And student generation number 5, for example, have the distilled knowledge of what the teacher understood after 5 epochs. But it also could forget stuff, right? It's not like a continuous improvement. So there's no better student. But what we assume that in inference, in real time, we're going to take all these student models and we're going to average their output, and it's going to be similar, at least as like the teacher model. So we're going to trade here one large model with multiple smaller models, which are much more efficient in resources, and we can run them in parallel. So the overall latency is going to be like run of the student model. Another method to do that is called online distillation. Online distillation, we don't have a teacher model. We only have student models. Let's say we have a data set and we want to train it on a small model. So instead of just training one model in the data set, in parallel, we're going to train several small models. And we're going to have a distillation loss that we're going to use at the end of each epoch or batch, depending how you want to implement that, that will distill from the better student to the rest of the students. So students could be, for example, the same model with different hyperparameters, or different models with different architecture, right? Doesn't matter. But you can think about it as a learning group of students that advise each other while they are learning. So the better model at the end of each epoch will distill his knowledge to the less accurate students, right? So those two concepts are the same concept of distillation, but when we train our models. And again, we affect the size of the length and the size of the number of parameters.
Question.
Yeah.
So going back to self-distillation, you just add up the epochs, results of the epochs, right?
Mm-hmm.
But has anybody suggested a weighted addition? Because our assumption is the later epochs are better.
Yeah. There's several different methods to do that, and yeah, definitely you can weight them based on the time, based on which epoch they've been. You can weight them based on the average accuracy of each student and so on. So yeah, there are different methods to do so. And the question was if there is a weighting mechanism we can add to that. Right. So going back to quantization, we can have what we call quantization aware training, which is basically making our model more robust to quantization errors. It's not replacing the static or dynamic quantization that we discussed earlier. It's just going to make it more robust. How we do that? During training, after each layer or if each calculations we do, we quantize and dequantize back our weights. So as we do that, we actually introduce here quantization error, right? Now, since this is during training, we actually using our loss function to make the model more robust, because those errors will propagate to our loss function at the end and will be fixed back when we do the backpropagation. So by doing that, our model become more robust to those two techniques of quantization discussed earlier. Makes sense? Yeah.
Just a clarification, dequantizing means I just take whatever my rounded value is and put it back in the float, or am I like adding a little bit of noise to simulate a reverse roundup?
No, it just means scaling back, but maybe adding noise could be a good idea. I know I didn't see a paper talking about that, but it mainly means scaling that back. All right, so we're gonna again impact the well, in training we don't see that, but afterwards we're going to pick the float size when we do it in runtime. So the next group of techniques to improve fine-tuning is called parameter efficient fine-tuning. There are many different methods to do that, but you can categorize them into four main methods. Additive, that means we're going to add something to our network. Selective, we're going to select which part we're going to train and which not. And reparameterization, which means we're going to calculate our parameters in a different way. And of course, there are hybrid methods which can combine some of them. Right. So here we're going to inference only on the trainable parameters. That means the size of the model will be the same, but the number of trainable parameters will be less. Therefore, the training will be much more efficient. And I want to focus, this is only relevant to fine-tuning. That means we assume we already have a pre-trained model that will train on language and so on, and we just want to fine-tune that on our data set. For example, we have this Llama 405 million parameter, sorry, model, but we don't have this $10 billion cluster like Facebook have, and we want to find that on data. So how we find that more efficiently? So additive means we're going to add something. So the basic assumption is that we're going to freeze all weights except something. So adapters is a concept when we add layers, fully connected layers, after each transformer block. That means we're not going to teach the model, the attention mechanism and so on. We're going to teach that our task. We're going to use those additions of feed forward to learn how to adapt the model output of each layer to our task, right? So we're only going to train those fully connected networks that are very small instead of training the entire transformer. Prompt tuning is another technique, which is more specifically to NLP because it's assumptions, but we assume that we could add to a prompt special tokens that we can learn only them. Now, the concept of prompt here is not the logical or textual prompt. Like there's a whole bunch of works on prompt engineering, like how to improve the prompt from the language point of view. Here we treat prompt after they were decoded. That means the prompt is the first layer matrices of K and V in the attention mechanism, and we add those trainable parameters, and we only train them. So we adjust the prompt or adjust the input to fit the network instead of adjusting the network to fit the input. And the last concept is I to the power 3. And of course, by the way, I put all the papers on the presentation so you can later on, if you want to review them. And they did interesting research when they found strategic places within the transformer architecture to put activations or matrices of the attention to put scanning weights that we only train them. So it's a different places, but the idea that these are the more crucial places if we want to steer the model to our task without training everything. So this is the concept of adding things to a network and training only those things. The selective approach is that we freeze all the weights, but only train some part of it. For example, BitFit suggested we only train the biases. That's it. I know it sounds weird, but they show it works, at least on small scales. Yeah, just like that. Freeze and configure is a method or branch of methods that say, let's freeze part of the weights or part of the layers and so on and train only some of them. A very common method is to freeze the lower layers and only train the upper layers of a model. But you can also do it within a layer or within group of neurons and so on. You need to have some metric how to select those neurons. A very popular metric is to do a calibration dataset, like run the network through a calibration dataset and see which neurons affect more the output than others. But there are different methods. From my experience, in the industry, not in the academia, those methods work less than the adaptive. Adaptive is much more effective, and reparameterization is even more effective. But again, the concept is valid, and the works show that it's working. Now, reparameterization means we want to calculate our parameters differently. So the most famous method, I guess, is LoRa, low rank adaptation. And the idea here that we're going to decompose our matrices, the large, vast matrices of the attention mechanism, into smaller matrices. And by decomposing them, it will be much easier to calculate them. So I guess it's easy to see what is more easy to come up with is 5x5 matrix to train that, or train these two 5x1 and 1x5 matrices. Of course, this is easier. Of course, we're going to add noise because it's an approximation, but it dramatically reduces the amount of calculation we need, the memory we need, and so on, because we only upload those into memory, etc. And then in inference, we can combine the weight matrix to the lower matrix. So if to show it in more formal, this is the weights of the pre-trained model, and in full fine-tuning, we're trying to learn some change of that weight, and then this is our fine-tuned model, right? So in LoRa, we have the weights of the model, and we're trying to learn two matrices that their multiplication will be the same size of the original change weight. And this dramatically removes memory consumption, as you can imagine. And there is a concept of ranking has an hyperparameter that means how much we want to decompose. The smaller the matrices, the less memory we need, but the more error we're going to introduce, of course. So the rank of the LoRa is a super important hyperparameters in that sense. And of course, as you can imagine, based on that, people suggest many different things. So you can take that to be more and more nuanced. And Corona, for example, suggested to decompose the matrix in another way. And there are many matrices and many methods to do it in different concepts. But the idea in the end is just train small matrices that will have the same size of what we'll do in fine tuning. So yeah, already implemented in a library called PEFT, which is parameter efficient tuning, fine tuning, and you can just have a lower configuration. The rank is the pulled apart. There are other things come into play, but this is the main idea. And if you want to implement that yourself, it's fairly easy. You just need to have the input and output dimensions and the rank that you care about. So we can create an 8 matrix is the input times size on the rank, and the rank on the output dimension. That means if we multiply them, we're going to have the input times the output in size, and we're going to have some sort of a hyperparameter for weighting. And then in forward, we can just multiply the input with the A and B, which should be the same size, would be the same size as the original weight matrix if we do full fine tuning. All right. Questions about LoRa? Oh, I didn't say that there is QLoRa, which is LoRa, and we quantize the matrices as well. So an example of how you can combine methods. Yeah. Any question on that? All right, great. So final notes. Efficiency is both engineering and theory. It's exactly when computer science and data science meet. I think there are places for both. Some of the most advances that we have in efficiency comes from very good engineering without changing the theory at all. And some of them are more theoretical in nature. There's a lot of room to improve. By all means, all the methods I presented does not mean that we have efficient LLMs. We don't have efficient LLMs. We just have better inefficient LLMs. So if you have ideas or want to research that, it's a very interesting domain. There are many methods I didn't cover, of course, as this is an overview. And the devil is in the details. I mean, some methods can be combined, and I put here some names here. You can read after if you like that combine very well. For example, parameter efficient tuning method and so on. But some undermine each other. So you need to be careful if you try to combine those methods. One thing about reading papers, so I guess, benchmarks are only good for benchmarks. I saw papers that presented very good on the benchmark, but in real life didn't work well, and so on. So my advice is not just to pick the best papers as is decrease the best memory and so on. Try it on your data. And of course, this is just an overview. So I simplified stuff to get the main point. So I put all the papers in there so you can dive in. Yeah, that's it. I have a few more minutes to questions if you have. Yeah.
This is excellent talk. Thank you. I'm wondering if this literature, like model compression, knowledge distillation, if this literature talks or overlaps at all with the traditional kind of compression literature from computer science. As you know, this is kind of in some ways a form of compression. So how much overlap are they two different to share ideas?
The short answer is that I don't know. The longer answer that quantization is very much inspired by the same concept that we have in compression, but I'm not sure. I'm not sure if someone did this reference. I don't know. Interesting. Any other questions?
Maybe it was implicit in some places. I was just thinking there wasn't a lot of simplification on the basis of interpretability or explainability. You can imagine with language models. I mean, if you think back to like Deep Dream or something, they're like, oh, I'm trying to figure out this node means this, and therefore, right? So, I'm just wondering, is there any active research arm that's making any progress with like, oh, in this 4th out of 17 attention layers, I have a semantic understanding, and therefore no one's compressed.
Yeah, so there is work on that. The question was about if we can use explainability in some sense to select which layers or neurons we want to compress. So yeah, there is work on that, both in knowledge distillation, that we can use distillation loss only for specific layers or specific areas, mainly with a calibration data set. Then you run them and you see which neurons more affect the accuracy. And in quantization, there is a method, actually, I think I put it in this paper, that suggests, let me see. There's a paper that suggests that, activation aware weights quantization that suggests to find some metric of which are the most important weights and don't quantize them, keep it in high precision. Now, what is more important and what's the explainability here is the hardest part. So there are ways to do explainability, but it's still not that accurate. So
yeah, I guess if I just press a little more on that, in vision, it's much easier to figure out that there are certain directions you're talking about accuracy as a percentage, but it also matters what your residuals actually are. Right? In vision, there's residuals that don't affect human perception at all. Same thing with your language. Maybe it's really hard to figure out what they are. That's kind of what
well, exactly that. It's hard to figure out what they are. I mean, they'll work on that. Anthropic did a very extensive work on their model. They present that. They try to figure out part of the network, what they're meaning, if they're reasoning or even attending to specific topics or stuff like that. So, but I think we are very early stage of explainability to effectively use that in such methods. Yeah, but I hope it will be in the future. Right. Thank you.
Thanks.
Thank you, Omri.
There weren't any questions on Zoom.